Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the next chapter, that is complex powers. So first of all, before starting this chapter, I want to say a big sorry to you guys. माफी कर दो मुझे because I made a huge mistake in the previous videos, which was not that important. That definition was not that important, but I will explain here what I mean by my huge mistake, what big blunder I have made. So previously, today, of course, we will discuss about instantaneous power, average power, RMS, all those things we will discuss from basics to the highest level. But before that, let's start with the mistake that I have made. So in the previous lectures, in the phasor diagram lectures, there I have told somewhere that the power factor angle was actually theta I minus theta b. That was my mistake, and there I told that the power factor angle is equals to the impedance, is equals to the admittance angle. So I'm sorry for my mistake. It is not actually that the case. And also the power factor, right? The proper definition of the power factor I will explain once we will go more deeper into the complex power. Actually, the proper definition of power factor is not this. This definition of power factor is only valid for single frequency components. So as we dive more deeper into the concepts, there we will understand this. So if you have forgiven my mistake, make sure to put, write down in the comments below that you have forgiven me, and yeah, that's it. You have, then I will be very thankful because I made a big blunder there. I just told you that it is equals to admittance minus impedance. So these definitions are not that important because these, right, it could have been it could have been current angle minus voltage angle as well. That could have been the thing as well. But the proper definition of power factor I will explain as we move along the chapter. So what important fact you have to remember is wherever I have made the changes in the notes, but those I have not updated while sending it. So just in your own notes, right? If you are making your own notes, just do one thing, that write that your power factor angle is equals to theta v minus theta I, okay, which is equals to the impedance angle is equals to the theta z, which is equals to minus of the admittance angle. That's it. But this definition is valid only is valid only for single frequency components. Okay, it's only valid for single frequency component. That's it. Like, what is the definition for multi-tone signals? That also we will see as we move along. So let's start with the basic understanding of power. Okay, what is power? Power is basically the multiplication product of voltage and current. That is what we know, right? But this was in DC, and in DC everything was constant, and if everything is constant, then power will also be constant. But in AC, my voltage is a alternating signal, my current is also a alternating signal. So if both are alternating in nature, the product also will be alternating in nature. Now you might have a very basic question. Then sir, whatever power the source is delivering, same power we are delivering, so net power, like the source does not deliver net power. No, you're wrong. You're wrong. Because there is a phase angle between the voltage and current. From there the net power comes. Okay, we will obviously discuss about the product. If let's say there was no phase, if there was no zero phase, right, then the voltage equation and the current waveform will be identical. So if there is no phase, that means positive times positive, I will get a positive number, and whenever I reach negative, my current also goes to negative. So negative times negative, again I get a positive number. So power is always positive if there is zero phase difference. So that is for purely resistive load, power will be always positive. But for inductive and capacitive loads, power might sometimes go negative. Power might sometimes go negative. So there is an issue, there is a problem. That's why when you try to start a motor or any components which has inductance in it, it gives, like whenever you start a motor, right, it gives you some kickback, it gives you some force. After just starting a generator, it forces you backwards, right? Who is generating that power? Inductor is like supplying the power to you. He is like pushing you, fighting. Okay, so inductor is fighting. Inductor has some power that it is delivering. So how it happens, how the power transfer happens, that also we'll see. And of course in resonance, the concept of power transfer we will see more clearly, how that power transfer happens between inductance, capacitance, like that. So the definition of complex power is a crucial concept in AC circuit, combines real and reactive power. Don't worry, I know you don't understand what is real and reactive. That is why we are studying this chapter. We will understand this real and reactive power, and this reactive power and real power, these we discuss only for complex quantities like inductance, capacitance, and like which have complex impedance, RLC. If it is a purely resistive impedance, right, then we don't need to talk about reactive power. We just talk about real, the active power, the real power. Okay, so we'll discuss about all this, don't worry. So the definition of instantaneous power, this you already know. What is the definition of instantaneous power? It is the product of the voltage and current. So my voltage is this equation, let's say if Vm sin omega t plus theta v, and my current is this equation, Im sin omega t plus theta I. So what will be the power equation? So the power equation will be Vm Im sin omega t plus theta b sin omega t plus theta I. This is the instantaneous power. This equation is the instantaneous power. And if I generally what we assume is we assume theta v to be 0. We assume theta v to be 0 and theta I to be my phi, the power factor angle. That's it. Okay. So now let's do a analysis in the table. Let's do a analysis. Basically, let me delete this page. In the table, if I come back, okay, for different values of omega t, how is the voltage waveform? How is the current waveform? Like, is it positive, negative, and what about the power? So if I vary from 0 to 5, okay, if I vary from 0 to 5, then what is the voltage? So if you see the voltage, right, is always positive from 0 to pi. No matter what, from 0 to pi, the voltage is always positive. So the voltage is always positive basically. Okay, so my voltage is positive, basically my Vin is greater than 0. Okay, what about the current? So my current from 0 to 5, if you observe, I have added a lag to my current, right? Current lags, basically it is an inductive circuit. So if I see my current basically is negative initially. From 0 to 5, it is negative. So I will say my current is negative. So what will be the product of a positive and negative number? It will be a negative number. So my instantaneous power for the duration of omega t equals to 0 to 5 will always be negative. That's it. Okay. So for omega t equals to phi to pi, next what is happening? For omega t equals to phi to pi, my voltage is again positive. So voltage will be positive. Voltage will be positive. What about currents? So my current, if I see, current is positive also. Current is also positive, right? From phi to pi, current is also positive. So it is also positive. So positive times positive will be a positive power. P of t will be greater than 0. Okay. Then from pi to uh, pi basically. From pi to, sorry, not pi to pi, pi to pi plus phi, because from pi plus phi, right, this is negative, and from pi plus phi this is negative. Why? Because like I have shifted this one to the right by 5 degrees. So if I have shifted by 5 degrees or radians, whatever you want to say, so if I have shifted by 5 radians, then everything will be shifted. So this value was supposed to go to 0 at omega t equals to pi, but I have right shifted everything by phi. So this point also will be right shifted by phi. So it will go from pi to pi plus phi. So this value will be pi plus phi. So here I will be at pi plus from pi to pi plus phi. My value, a voltage will be what? Of course, after pi, right, my voltage goes to negative. So voltage will be negative after pi, but current is still positive till pi plus phi. Current is still positive till pi plus phi. So again my power will be negative. Again my power will be negative. Again from pi plus phi to 2 pi, my voltage is what? Voltage is always negative, right? In after pi, voltage is always negative. So voltage will be always negative, and after pi plus phi, current is also always negative till 2 pi. Current is always negative. So current is also negative after pi plus phi. So what is the product? Product of the voltage and current is positive. So if you see, for certain periods the power is positive. For certain periods the power is negative. For certain periods the power is negative. So for certain periods the power is positive. Okay. So Yeah, that is the case. So basically, right, instantaneous power can be positive or negative depending on the phase difference between the voltage and current. It can become negative in complex networks due to presence of inductance and capacitance because they have energy storing capability. So what they do is they store the energy, and after a while they again send back the power to the source, and then again it oscillates. Then again the source sends the power to the inductor, and then again the inductor sends the power back to the source. And you might have a question, then what's the point? व्हाट्स द पॉइंट? अगर मतलब ऐसा ही करना था, खेला खेला कि मैं फेंका इसको, उसको उसने पकड़ा, फिर उसने मेरे को फेंका, तो इसमें तो लाइक बेसिकली वी हैड वेस्टेड आवर एनर्जी, राइट? Like there is some like if the current is flowing from point A to point B in the resistor, right, some energy heat is getting dissipated. So what is the point of that energy transfer? Because ultimately source is getting back the same energy, then again it is sending the energy. What is the ultimate point? The point is these components actually have special features. आपको पता है राइट, कुछ कुछ चीज़ों में स्पेशल फीचर्स होते हैं, इसलिए आप यूज़ करते हो, इसलिए आप उसको यूज़ करते हो। जितना भी लाइक वट एवर द प्राइस ऑफ इट इज, वट एवर हाउ मच हाई द प्राइस इज, इट हैज़ सम स्पेशल फीचर्स. So inductor and capacitor also have some special features. What is the special feature of inductor? It does not allow change in current. Also, it helps to generate flux. So inductor basically helps in generating magnetic flux. So L helps in generating magnetic flux, and magnetic flux, trust me, is a beautiful little thing, because with magnetic flux everything is made. Your fan, your whatever you see rotating parts, any rotating parts you see nearby your home or any place, right, it is mainly due to inductor. So why? Because inductor generates a flux, magnetic flux, through which we are able to generate the rotational motion. So inductor generates magnetic flux and capacitor generates what? Capacitor generates electric flux, charge, right? It is used for storing charge. So it has also its use case in what? In electronics, in semiconductors. Capacitors are used hugely. So both of these have very special things in them. But of course, with any special thing, there comes bit of terms and condition. Like if you've got a girlfriend or a boyfriend, right? Of course, like that person is very special to you, but there are few terms and conditions which both of you have to mutually agree on, right? So that's why inductor and capacitor also say I'm special, but I have few terms and conditions that you have to agree. Okay, if you don't agree, then get lost, bhar mein jao. Okay, so of course you have to agree, we have no choice, right? You have to agree. So yeah, so that is the thing here basically. So yeah, we will discuss more about this once we move on to machines and those topics. Okay, so like because many students have this doubt, and I know you also have this doubt, that why is it important? Like is it like if it's just there is energy transfer happening between source and load, then what's the point? So I wanted to clear this at the starting of power itself. Okay, so this basic thing I hope you have cleared. Now let us calculate one more quantity. So this instantaneous power, right, is not a very good representation of basically a quantity that I want to say. Basically, a circuit contains R, L, and C, and I want to say that how much power is it consuming, or how much active power is it consuming, or how much actual work is it doing. How can I quantify that thing? So engineers came up to an idea that let's do one thing. Our power, right? Our power graph is always oscillating. So if I draw the power graph, it will always like it will be sometimes positive, sometimes negative, like that. It will also be like a sine only, but its frequency will be 2 omega, because if you know, if I multiply two sines with frequency omega t, I get two terms. One is 2 omega t, other one is only with theta constant. I will obviously derive that, don't worry, I will derive that. So in that case, that is not a very good quantity to represent the circuit in terms of power. So what we thought is actually make another quantity known as average power. Average power is also known as the real power, because this is the actual power that is getting consumed in the circuit. Basically the resistive elements are consuming this power. Okay, we will discuss more about this, don't worry. This real, active, all those things we will discuss, you don't have to worry at all. For now, just understand average power is basically the DC power. DC means what? Average. DC means basically average. Okay, so average power is the average of the instantaneous power over a complete cycle, because my power is like it is repeating over a complete cycle, right? Power, expression of power, it is always repeating over a cycle. So basically I just want to take the average, that's it. Okay, so that is the case over here. So yeah, I have 2 sin A, sin B, cos A, like this is the formula of p average, this comes out to be this. Of course I will derive it, don't worry, I will derive this thing, okay, how it comes out. So one formula, I hope you know, basic trigonometric identity, that 2 sin A sin B is cos A minus B minus cos A plus B. That's it, the trigonometric identity, I hope you know. So we will do the average. Basically, what is my instantaneous expression for instantaneous power? What is the expression for instantaneous power? The expression for instantaneous power is what? The expression for instantaneous power is Vt into It. Okay, Vt into It. What is Vt? Vt is Vm sine omega t plus theta v. And what is It? It is Im sine omega t plus theta I. Okay, so we will use this identity. So this will be my sine A and this will be my B. Now you might have a question, sir, why did you choose this one A and why did you choose this one B? You could have done this one as A and this one as B as well. You could have done that, right? Why not this? Because that's how, like, who have derived it, that's how he did it, right? That's how he did it. So if I take your question, right, if I would have chosen this as A and this as B, then my definition of perfect angle would have been that which I have mistakenly given to you previously. It was theta I minus theta V, previously what I have told you, right? So I hope you understand there is ambiguity, like whether I have to, like whether the perfect angle is theta I minus theta V or theta V minus theta I. So don't go into the ambiguity. Actual definition of power factor is not even this. Once we will go deeper into the chapter, I will tell you what is the actual definition, actual physical significance of the power factor. Okay, and that will be always valid. That will be always valid. In this case, we have a same frequency component. That's why this definition also comes. So here, this is A and this is B. So ultimately, my what does my Vm Im comes out to be? So my Vm Im, this comes out to be like cos A plus cos B, right? It is 2 sin A sin B equals to cos A plus cos B. So what I can do is multiply divide by 2. So if I multiply divide by 2, then it will be 2 sin A sin B. It will be 2 sin A sin B, and then first number will be cos A minus B. Cos A minus B is what? Cos A minus B is what? This is A and this is B. So ultimately it comes out to be theta B minus theta I minus cos A plus B, minus cos A plus B. What is cos A plus B? Cos A is omega t plus theta V, cos B is omega t plus theta I. So it will be 2 omega t plus theta I 2 omega t plus theta I plus theta B. Okay. So now from here, if you notice, we are getting actually two terms. So if I break this down, if I open the brackets, this will be Vm Im by 2. So this will be cos theta B minus theta I minus Vm Im divided by 2 into cos 2 omega t plus theta I plus theta B. Okay, so here if you see, one of the term is time independent. It is constant. Basically, it is not dependent on time, right? It is just a constant value. Theta V minus theta I is a constant thing. Vm Im by 2 is a constant thing. Cos of theta B minus theta I is a constant thing. Now this term is actually time varying. And with what frequency does it vary? If you observe, it is varying with 2 omega frequency. So actually I have a constant term, over it I have a varying term. So the graph will be somewhat like this. Okay, so graph of P of t, instantaneous power omega t, it will be somewhat like this. I will have a constant term, over it I will have this cos term which is oscillating always. somewhat like this, okay, which will always oscillate here, somewhat some always oscillate. So the ultimate resultant power will be the superposition of these two graphs, constant and the oscillation term, with 2 omega. Remember, so your power oscillates with 2 omega if I have a current and voltage signal with frequency omega. So power varies more faster. So if my current frequency, if our source frequency is 50 hertz, so power will go from positive to negative 100 hertz with frequency 100 hertz. So that's why you don't notice it. Your lights, everything, right? It is always flickering. It is always flickering, but your eyes are not able to notice that because they are so fast. They are flickering so fast. They are dimming and then brightening up so fast that you are not able to notice it. You are not able to notice it. So that is the difference between this and that. Okay. So yeah, that's why you don't notice it. So basically, here are the two figures. One is this constant one. Another one is a time varying one, varying. Okay, and of course this is with the negative sign, right? This is with the negative sign. So if it is with the negative sign, simply I have to invert the graph. Simply I have to invert the graph. If I invert the graph, then it will be like this only. Okay, so yeah, now here is the, like, this is the graph which is the superposition of all of this, right? It is the constant term, that is half Vm Im cos omega theta v minus theta I, and then the oscillating part. Now important part to notice here is power is mostly positive. In this case, power is mostly positive, but it will depend on the values of theta I and theta v. It can go negative as well. It can go negative as well. Power can go negative as well. Okay, but mostly it will always be positive. Why? Because I have a resistive component there. If I have a resistive component, ultimately it will consume some power. Ultimately it will consume some power. So how can you understand overall is my source delivering or absorbing the power? Of course, Himanshu has already taught you that you see the graph area, right? If it is the positive portion, if it is the positive portion of the graph, then that means basically the power is going from source to load. Whenever the instantaneous power is positive, power is going from source to load. Whenever the instantaneous power is negative, the will go from power will go from load to source. Power will go from load to source. That's it. So it really depends what is the type of power, like what is the sign of the power. Okay, and what is the average basically? So average, right? This is the expression for instantaneous power. This was the expression for instantaneous power. Now average will be integrating this whole equation and then dividing by time period t. That's it. So my P average will be integration of my instantaneous power, integration of my instantaneous power with respect to t over a whole period divided by time period t. 1 by t. Okay. So what is it? So if I integrated this thing, right? If I integrated this whole thing, what you observe is this thing, right? This average of this is what? Average of any sine signal, cosine signal. What is the average of any sine or cosine? Its average area is 0. There is no area under the curve. Whatever the positive area, same area is the negative. We can integrate, correct? And so ultimately this is time varying and this is sinusoid. So this is vanished out. Only this term is present. Only this term is present. Okay. So if I integrate this term, right, this will come out to be 1 by t integration of, I will copy this whole thing. Okay, this is dt, this is dt. So of course this integration will be simply 0. I hope I don't have to explain what will be this is integration. So Vm Im to cos of theta b minus theta all are constant, all are constant. So it is simply integration from 0 to t and divide by t. So it is simply t by t. So ultimately the value that comes out, that is my P average, is Vm Im by 2 cos of theta v minus theta I. This is the ultimate value that comes out. Now we can further, what we can do, we can further rewrite this as this, that it is equals to Vrms by root 2, not sorry, not Vrms root by 2. So basically it is equals to Vm by root 2 Im by root 2 into cos of theta b minus theta I. Okay, so this is my p average, basically this is my p average. So from here we make another we make another relation that this I will derive as well, that my RMS value of any sinusoid quantity is what, root 2 divided by the amplitude. So this is what, this is root 2 divided by the amplitude, that is Vm. So this ultimately becomes Vrms, this becomes Irms into cos of phi. Phi is the power factor angle. So this, right, I think you have seen already, you know already this about this formula. So I don't think I have to like say about this formula. Of course, this is a very important formula, and how it came, we derived it from scratch. Okay, so for passive networks, this value, right, for passive networks, my phi has to be between, phi will be between 90 degree to minus 90. This I have already explained why it will be between minus 90 to 90. This I have already explained. It will only lie on the first and the fourth quadrant. It will only lie in the first and the fourth quadrant. So this is the case for a passive network. So what you understand is basically that means your cos of phi, right, will always be positive. So that means my average power will always be greater than or equals to 0. It cannot be negative. So important conclusion is, for passive loads, active power is greater than equals to 0. For passive loads, active power is greater than equals to 0. Okay, so that is what I have written in the key points. P average is positive for passive circuits. It can be negative for active circuits. We'll see that as well. Okay, if theta v minus theta I exceeds 90 degree, and that is only possible for active circuits. And I will not explain why is my range of phi like this. All the basics have been cleared very well in phasor diagram. So I will not explain here why the range of phi is like this. If you are not able to understand, please go back and watch the previous lectures. So that's why we generally write our power as Vrms, Irms cos phi, because we don't want to write this extra 2 term, right? That is like our what do you say? क्या बोलते हैं उसको? आलस, laziness. That is our laziness basically. We don't want to write this 2. So to avoid writing the 2, basically what we did, we written it in terms of RMS value. Okay, that is the main reason. Okay, so I that was the few explanation about the power. Now I want you to give this as a homework. I want you to try it out by yourself, and then I will solve. Like very basic thing, you have to calculate the instantaneous power expression. You calculate. Okay, how I have derived using V of t, I of t. You calculate, and also you calculate the average power. What will be the average power? Like there is a formula. Don't like, obviously you can use the formula. Don't directly use the formula. First derive the instantaneous power. Then from there you derive the average power. This only you will do once in your life. Then of course you will remember the formula and apply the formula, that I know. But for the first time, right, you should at least try it out. You should do it by yourself. Okay, so that was the homework for you. This was the assignment homework for you. Okay, so let's start with the this few things about the average value. So average value, you already know what is average value. It is basically the mean, like overall summation of x of t. Like let's say I have samples like this, x of t. Like if I have a sample, right, which has 3 values, 1, 3, 5. So what is the average? What do? You just add all the values, that is In our case, it is 9 divided by 3 divided by the number of total elements in that set. So it will come out to be 3 only. It will come out to be 3 only. Okay, that is it. Very basic thing. Okay, mean, I hope you know. For this is for the discrete variable. For continuous variable, it is simply integration. So I have already used it. So we will derive few average values of few standard waveforms. Also, we will derive the RMS value. So this was the average value. What is the RMS value? So RMS value is basically the root mean square. So I will delete this page. RMS value is here. It is defined as the root mean square. Basically, what we do, we first square. So first, what is your first task? You have been given a waveform or a function. If you want to find the RMS value of that function, you will first task will be first to square it, then to take the mean, of it, then you take the mean of it. Okay, then you take the mean of it. Then what you do? Then you take the under root. This is the third. Then you take the under root. Okay. So this is basically root mean square. Or this is basically root mean square. So mathematically we define it, and we will derive the root mean square for few standard values. For sinusoidal, it is Vm by root 2. For a sinusoidal signal, it is Vm by root 2. Okay. So we will basically, of course, we will derive. Before going into that, one thing I wanted to say is basically for a what do you say, this orthogonal signals. So I will discuss about orthogonal signals, then I will discuss about the other fact that I missed out previously. Okay. So what are orthogonal signals? Don't worry, you will learn about orthogonal signals in signals and systems. So orthogonal signals are basically the signals in which there are two signals, let's say x1 and x2. Their inner product is 0. That is what orthogonal is. If their inner product is 0, then they are known as orthogonal. But this was the bookish or the language written definition of orthogonal signals. But what about the mathematical definition of orthogonal signals? So the mathematical definition is somewhat like this. It is equals to integration from 0 to t x1 of t into x2 conjugate of t equals to 0. Now here we assume that our x1 and x2 can be complex signals. That's why there is a conjugate. We will discuss about real signals as well without the conjugate formula. So for periodic signals, the definition of orthogonal signals is something like this. I take the product of x1 and then take the complex conjugate of x2, then multiply those two, then integrate over 0 to t, and if that integration comes out to be 0, that means it is a orthogonal signal. What about the aperiodic signals? So these are all my periodic signals. These are all my signals, and these are my aperiodic signals. These are my aperiodic signals. Okay. So there are few examples of orthogonal signals like sin omega t and cos omega t. How can I verify? So basically what you do, you just integrate sin omega t into cos omega t, because these are real signals. I don't have to like take care of the conjugate, because conjugate of any real signal is the same signal only, it does not change. This is the property of conjugate. So now if I integrate over the period, what is the period? Is 2 pi, right? Both of them are periodic with period 2 pi. You will observe that the integration that you are getting is 0. So what is the graphical definition of orthogonal? Basically, whenever I multiply these two signals, right, what happens is that their product is, for certain region it is positive and for certain region it is negative, and for the same region it is positive and negative, right? For the same region it is positive and negative. Okay, it is positive and negative. Basically, their overall area comes out to be 0. Their overall area under the curve comes out to be 0. That is what an orthogonal signal is. Another very good property of orthogonal signals is like these two signals are also orthogonal. Why? Because two sinusoids or cosinusoids with different frequencies are always orthogonal to each other regardless of their phase difference. So here the phase difference between these two sinusoids, because they had same frequency, their phase difference needed to be what, 90 degrees. That's why they were orthogonal. Because their phase difference was 90 degrees, that's why they were orthogonal. But here what is the phase difference? You cannot comment about the phase difference when frequencies are different. When frequencies are different, you cannot comment about phase difference. There is no concept of phasor diagram. When frequencies are different, there is no concept of phasor diagram, because I have told you we draw the phasor diagram for a constant frequency, and due to that only, with respect to that frequency only, we draw all the other vectors or all the other phasors, because the information about the frequency gets lost while drawing the phasors. Got it? So that's why there is no concept of phase difference here. I cannot comment, we cannot comment, I will write here, we cannot comment about the phase difference okay of the we cannot comment about the phase difference here. Because why? Because the frequencies are different. Okay, because the frequencies are different, we cannot comment about the phase difference. So that's why always remember, if I have two sinusoids of different frequencies, regardless they will be always orthogonal. Regardless they will be always orthogonal. Two sinusoids of same frequency are orthogonal. If there is, like, if I have two sinusoids but they have same frequency, they also can be orthogonal, but a certain condition needs to be met. What is the condition? That their phase difference must be a multiple of 90. Their phase difference must be a odd multiple of 90 degrees. If there is a phase difference that is odd multiple of 90 degrees, then they are orthogonal. But one thing, important thing to notice here is, in network theory we are only concerned about real signals. You will be learning more about complex signals in signals and system. So if we are mainly concerned about real signals, basically what happens, my conjugate of x is equals to x, because there is no imaginary part, there is only real part. So basically what happens is this, right, the conjugate sign goes away, because I know you guys fear whenever you see something complex expression like this, conjugate conjugate term. Okay, so that's why we can simply write our orthogonal relation like this. For a periodic signal, it will be x1 of t into x2 of t, simple product, plain product, dt equals to 0, and for periodic signal it will be x1 of t, x2 of t over a whole period equals to 0. Okay, so this was a quick thing about orthogonal signals and why they are important to us. Why they're important? They're important because if I have a signal x of t which can be written like sum of different signals, x1 of t, x2 of t, x3 of t, then I can directly compute their RMS value if they are mutually orthogonal. If they are mutually orthogonal, then I can directly compute their RMS value. How is it possible? How is it possible? I will prove it to you. I will prove it to you if we know that these three signals are orthogonal. Or let's, for now, let's take a simple example. X of t is equals to x1 of t plus x2 of t. Okay, and these two signals are orthogonal to each other. Assumption is my x1 of t and x2 of t are orthogonal to each other. Okay, so we will see about this. So how do you calculate the RMS? That I have already told you, right? How you calculate the RMS. So first thing is, let me write down the RMS values of each individual signals. What is the individual RMS value of x1? It is simply what have I told you first. You first take the square. RMS square comes first. So you square the signal first, x1 whole square of t dt. Then what you do? Then you take the mean. So this will be 0 to t 1 by t. Okay. Then you take the under root, square root. Then you take the square root. This is the RMS value of x1 of t. What is the RMS value of x2 of t? RMS value of x2 of t is this. Same thing only, 1 by t 0 to t x2 whole square t dt. Okay. So these are the RMS values of x1 and x2 of t. So now let us come to the real point, is how do I compute the RMS value of xt, normal xt. So for RMS calculation, what we do, we first square. So again I will square on both sides. If I square on both sides, this will be x square of t equals to x1 whole square t plus x2 whole square t plus, of course it is 2ab, right, plus 2ab. So it will be 2x1 of t into x2 t. So now next, what is the step that we do to calculate the RMS? We take the mean, right? We take the mean. So if I do the mean on both sides, 0 to t, this 0 to t, and of course I will divide by t, of course I will divide by t, and dt also will be there, right? Dt also will be there. So let me use some other color only. Plus 1 by t of integration, this 2 can come outside, x1 of t into x2 of t dt. Now of course I have told you what is the initial assumption. Initial assumption was x1 and x2 of t are orthogonal signals, of course, which are also periodic, are periodic orthogonal signals, periodic orthogonal signals. So if that is the case, then what can I comment? I can comment that this, right, whole thing will be 0 because they are orthogonal. Because they are orthogonal, this whole thing will be 0. So ultimately this, right, this is what, this quantity is what, this quantity is x RMS, right? If I take the whole under root on both sides, of course it will be x RMS. And if I take the whole, like, what is this? What is this quantity? If I square on both sides, it will be x1 RMS whole square, correct? This whole quantity is x1 RMS whole square, that is present here. That is present here, right? This whole quantity is present here only, if I just square on both sides. So ultimately, my x RMS whole square is equals to x1 RMS whole square plus the same thing if you observe here as well, that if I square on both sides, this will be x2 integration 1 by t 0 to t x2 t is equal to x2 RMS whole square. Okay, so ultimately this is also equals to x2 RMS whole square. Okay, so this will be t, this will be t, this will be t as well. Okay, so from here, right, you can directly say that my x RMS of t is equals to x1 RMS whole square plus x2 RMS whole square t. So that is what I have written here, right? So all that is to just simplify this expression. If is to come to this final expression, because this expression is very very important to us, and we will actually use this expression later on. That's why I had to do this much of hard work. So before going into the next topic, just wanted to quickly do one thing that I missed previously. So I will move these pages right before this thing, because that is supposed to come here only. These pages are supposed to come here only. Yeah, so what we have to do is just hold on. Yeah, is one thing I wanted to say about for a purely resistive circuit. What is the thing with a purely resistive circuit? So let me take two things, two sources. One is the AC source, one is the AC source. Okay, one is the AC source and one is the DC source. So I will write here AC and DC. Okay, this is the basically AC source. This is the AC source. Sorry, this should not be the AC. I should first do the DC source. So yeah, I will copy this here, and this will be my DC source basically. Okay, so here what we observe is, what is my power? What is my power? Power in a DC source is very very simple, right? It is simply the voltage divided by current, because it is a constant DC value. Let's assume this to be Vm only. So the power in the case 1, this is the case 1 and this is the case 2. So in case 1, power in the case 1 will be what? Vm voltage whole square divided by R. Okay, Vm whole square divided by R. What about the power in the case 2? So case 1 is very very simple. What about the power in the case 2? If I see the power in the case 2, it is what? It is simply V of t whole square divided by R. This is what? This is the instantaneous power. This is the instantaneous power. But what if I write just P2? Whenever I write just P2 without any brackets T, that means I am discussing about average power. I am discussing about average power. So this will be equals to what? This will be integration. What is the Vm expression? So my Vm expression is basically equals to Vm sine omega t. So this will be Vm square sine square omega t into d omega t divided by 2 pi. I hope there is no doubt why am I dividing by 2 pi, why am I not dividing by time periods pi. Why is this in radians? Why? Because this d omega t, what is the unit of omega t? Radians. That's why if I multiply by radians, I should divide by radians. Ultimately, the unit of power should remain intact. That is voltage whole square divided by the resistance. That unit is still intact. So make sure that unit is intact. So what is the value of this, right? I will vary from 0 to 2 pi. I will vary from 0 to 2 pi. So this will be what? This will be basically divided by R ultimately this, what is the integration of sine square omega t, sine square omega t. So if I convert my sine square omega t, like I know you know this half, so but few students may not know, so you can skip this portion. So I know this formula, right? I always write in shortcut cos square t, cos square theta minus sine square theta is cos 2 theta. So I can write that from here I can convert basically my 2 cos square, so it will be cos square theta minus sin square theta. So cos square minus sin square, so this will be what, 1 minus sorry 1 minus sin square theta, so this will be 2 sin square theta is equals to 1 minus cos 2 theta. So sin square theta will be equals to 1 minus cos 2 theta divided by 2. Okay, so basic trigonometry I am doing. So now if I write this same expression here, I will integrate from 0 to 2 pi 1 minus cos 2 omega t divided by 2. D omega t is of course there, and of course if you know, whenever we integrate any cosinusoid or sinusoid over a whole period, now this is not even the period. What is the period of this? What is the period? It is like a power signal. The period is pi. So it does not matter if it's a multiple of the period. If I am integrating over a multiple of the period, basically the area will be 0 for this case, and of course I only have this term, that is half. So ultimately this will come out to be 1 by 2 pi, 2 pi of course will get cancelled. This will be Vm also is there, Vm square is a constant, so that will be outside. So it will be Vm square divided by 2r basically. Or what I can write, I can write this as like the definition of power is also that if in this source, if this AC source was, if this AC source was not there, this is also another definition of the power, that let's say this AC source was not there. If this AC source was not there, by what amplitude of DC source, what value of the DC source I will replace this AC source so that the average power remains constant. So I will write here by what amplitude I will replace the AC source so that the power remains same, not constant, power remains same in the previous circuit and in the current new circuit. So that is a definition, also another definition of RMS. So basically the DC quantity supply value will be some VRMS, right? VRMS voltage. Now if I calculate the power from this VRMS, so VRMS whole square divided by R should be equals to my actual power which I calculated with the AC source. So what was the actual power? It was Vm square divided by 2R. So basically your VRMS comes out, the root mean square value comes out to be Vm by root 2. So another definition of RMS is that RMS quantity is represented by, if I replace this source with its RMS value, which is a DC source, then it will also deliver the same average power as the AC source. If I would have replaced this AC source with a DC source whose amplitude is the RMS of this AC source, then that also will deliver the same power. So that is also another definition of RMS value. So another definition of RMS value. Okay. So I hope you understood, like although this is not the formal definition, but we also sometimes like we also compare RMS in terms of power. That is also what we do. So let's now compute the RMS of few standard signals, because they will ask you in gate, questions have been asked to find out the power with respect to few standard signals. So of course you should know how to find out the RMS of those standard signals. So the first one is basically the this square waveform. Very simple. If I have a square waveform whose x of t is a from 0 to t on, and then from t on to t x of t is 0, from t on to t x of t is 0 basically. So I can write basically, how do you calculate the like average? First I will calculate, the average. Average is very simple, right? How do you calculate the average? Simply you take the mean. It is a periodic waveform from 0 to t of that whole signal x of t, you take the mean of that. Okay, so this will be 1 by t, 1 by t into x of t. X of t is 0 to t. And what is x of t? So x of t between 0 to t on, it is a only. From t on to t it is 0. From t on to t it is 0. From 0 to t on it is a only. So this will be a from what? From 0 to t on. So I don't need to integrate over the whole period, because for the rest of the time it is simply from t on to t, it is simply 0 dt. Okay, so okay, so it's very simple to find out the average value. Average value will be a into t on by t, a into t on by t, that's it. What about the RMS value? So this was like very simple like this, right? You can further derive this, you can further write as a into, like this is also known as the duty cycle. If you will study power electronics from me, you will see there, this also I have derived as duty cycle. Sometimes t on by t, right? This whole thing is known as the duty cycle. What about we can further write this t on by t on plus t off. Okay, we can further write this t on plus t off, that's it. So that is the that is the average value. What about the RMS value? So RMS value is, again, what is the formula for RMS? The formula for RMS, x RMS of t is simply from like first I square that waveform. So if I square, right, for like this will be from 0 to t on, this will be a, so it will be a square dt, plus from t on to t, this will be 0 basically. And of course I first take the mean, then I take the under root. Okay, then I take the under root. So this will be equals to what? Basically this is a square is constant term, so it can come outside, it will be a outside. This will be under root 1 by t into t on. Okay, other part is 0. So ultimately this comes out to be a into t on by capital T whole under root. This is the RMS value expression, and I would prefer if you remember it. Okay, of course it will not take you much time to derive, and it will not take you much time to remember as well, because the mean value was very easy, right? It is simply a into t on by t, and the RMS value is also very easy. RMS value is also very easy. So this is the RMS value basically, and if there is a very good relationship that if your T on by T, that is we have a 50% duty cycle, T on by T is 0.5, or other words we say it as 50% duty cycle, then my xRMS equals to A by under root 2. That is what my xRMS is equals to. Okay, so like very good relation that you can keep in mind. So what I will do is this triangle waveform. So this was the for the RMS value of square waveform. So this triangle waveform, I want you to try it out by yourself. I want you to try it out by yourself. So basic thing, you know how to find out the mean and how to calculate the RMS. So I want you to try it out by yourself, and in the next lecture I will derive the triangle, basically the expression for triangle, and also I will of course solve the question that was there, like it's a 1 second question only, and of course we will do few assignment questions. So basically we will do few assignment questions. So I think the PDF is already there, so those questions also we will do in the next lecture. So I hope you have enjoyed this lecture. If you did, make sure to hit the like button, make sure to comment down if you like enjoyed any concept, any particular concept. If you enjoyed, make sure to comment down below, and I will see you in the next lecture. Until then, happy learning.